For homework assignment number 11, you are asked to complete the following exercises. Beginning on page 161, you are asked to put each of the following statements into standard form as a categorical proposition, then construct a Venn diagram for the proposition. So let's begin with problem number 2. That's where we're going to begin. And let me get my trusty Alright, so problem number 2. The initial sentence you were given is some cats are friendly animals. And the first thing you had to do, you're beginning with problem number 2. So with problem number 2, the initial sentence you were given is no lie detector is perfect. No lie detector is perfect. And the first thing you had to do is put this into standard form. And it's pretty close to being right. The only problem here is you have to name a class in your predicate term. Just saying no lie detector is perfect. Perfect is an adjective. So you need a noun in order to name a class of things. So to put this into standard form, you'd say something like no lie detector, I'm going to abbreviate that, is a perfect, I ran out of space here, test. Or you could say a perfect thing, you could say anything you want, as long as it, as I've said in the past, makes sense with the sentence and that it forms a class of things. So no lie detector is perfect. You might say no lie detector is a perfect test. No lie detector is a perfect thing, is a perfect object. It doesn't really matter. So we just then have to Venn diagram this. And the instructions said you didn't have to put things into S and P. You didn't have to use those letters. You could just use abbreviations from the sentences you were using. So we could use LD for lie detector. We can use PT for perfect test. We have our regions. And the way we Venn diagram this is we say we shade in this region right here, region 2. And that's how we show no lie detector is a perfect test. There's no overlap between the two regions. All right. So number 3. You were given the following sentence. There are some fast turtles. There are some fast turtles. All right. And this is not in standard form. First of all, notice that the quantifier is occurring right here. And remember, the quantifier has to come first. So to put this into standard form, I'm going to write standard form here so you can see. We're going to have to begin some. And then what are we saying? Basically, we're saying the following. Some turtles are fast. And we could say a lot of different things here, but we have to name a class. I'm going to say fast animals. You could say fast things. You could say fast objects. You could say a lot of different things. I use the word animals. You don't have to necessarily use that word, but you do need to name a class. You just can't say some turtles are fast. You have to say some turtles are fast objects, fast things. You can, pick the noun you want to use. And I'm going to use, we're going to use abbreviations from here. I'm going to use T for turtle. I'm going to use FA for fast animals. We have our 3 regions, and the way we demonstrate this is we put an X right there in region 2. And you know, hopefully this one's pretty easy, but if you ever get a little confused about how to do the Venn diagrams, I always like to use the numbers. The numbers really help me out because fast turtles right here, or let's just start with turtles. That's region 1 and 2. Region of fast animals, as I've listed, is 2 and 3. And what you do basically whenever you do the Venn diagram is you're only going to shade or X in the regions that you identify in the subject term. Those are the only 2 that you're ever going to worry about. You're not going to worry about the predicate. These are basically the regions that you state in your subject term. Those are limiting where you're going to shade or X. You know you're going to X because the word sum appears. Whenever the word sum appears, be thinking X. And what you do, basically the only purpose that the predicate term serves is to identify one of the regions. And so once we identify the regions where the 2 overlap, we can actually just disregard that region right there. We don't care about that. And when you see R, when you see sum R, you know to put an X in the area of overlap. If it said R not, you would put an X in the area where the 2 don't overlap. And so if it had said some turtles are not fast animals, you'd put an X in 1. But anyways, moving right along. Number 6. There are no gilled animals. There are no gilled animals. Okay? Well, the first thing we notice about this sentence is that the quantifier is not first. So we want to put the quantifier first. And what is our subject going to be? Well, our subject is actually going to be animals. This is what we're going to say. No animals are gilled, and we have to name a class. Hold on, I gotta erase that because I'm going to run out of room if I don't. So no animals are gilled. Still going to run out of room. And here we have to name a class. And you could name a lot of different things you want. You could say no. Oh, no wonder I'm running out of room. I just noticed I wrote the word animals twice. Some of you are just sitting there laughing at me. We could say a lot of different things that we want, but I'm just going to say animals here. We could say no animals are gilled things. We could say no animals are gilled creatures. No animals are gilled objects. I'm just going to say no animals are gilled animals. And we Venn diagram this. We come over here. I'm going to use A to represent animals. I'm going to use GA to represent gilled animals. And the way we diagram this is we shade in, whoops, I got a little out of my line there. We shade in 2. We shade in region 2. All right. So let's move along. So after number 6, you were also asked to do number 7. So number 7, all clocks tell time. All clocks tell time. And this one is pretty close to being in standard form. It has the quantifier first, which is good. But what we're lacking here is we haven't named a class in our predicate term. Also, notice we're missing the copula, R. It's not listed. So what we need to do is add a couple of terms here. All clocks are, and you could say a lot of different things. I'm just going to say devices that tell time. You could, if you wanted, have said all clocks are machines that tell time. All clocks are things that tell time, you could have used the key thing here, and I know I keep repeating, you just need a noun term right there. Notice tell time, that's not a noun. You need a noun term in the predicate so that you name a class. So we come down here, we draw our circles again, 2, 3. I'm going to use C to represent clocks, and I'm just going to use a D to represent devices that tell time. Now, how do we diagram this? This is the most tricky one of all. But remember, this is where our numbers come in to play. 1 and 2 represent clocks. The circle represents clock. 2 and 3. Now, what we do is the first thing we want to do is we want to identify the region of overlap. And then once we identify the region of overlap, just disregard the second region in the predicate term. And what we're saying here is we're saying all the clocks that exist are located within 2. So if all the clocks exist here, how do we represent that? We don't use an X because X represents sum, so that's not going to work. The only device we have left is shade, but shade represents empty. So we wouldn't shade in 2 because that would say nothing is in 2. And what this sentence up here is telling us is that everything is in 2. All the clocks are in 2. But if all the clocks are in 2, where are there no clocks? Well, again, there are no clocks in 3, but we don't care about 3. We're disregarding 3. We only care about 1 and 2 because those are the only regions where clocks represent or represented. So basically what we do is we shade in 1. This is how we do this. We shade in 1. And again, the reason for this is we're showing that all the clocks that exist are in 2. I know it's a little confusing because you're like, well, why don't you shade in 3? Because that would show that no clocks are there. But again, the reason we don't shade in 3 is we don't have to, because C, by definition, is limited to 1 and 2. You would never find, no matter what this quantifier said, you're never going to find clocks in region 3. Because it's just not possible, because C just is equal to 1 and 2. So you can't have any clocks in 3. So that's why we wouldn't do that. All right. So now we're on to number 8. And for this one, some cities are infested with crime. Some cities are infested with crime. All right. And this is close, but notice here, again, we haven't named, excuse me, we haven't named a class of things. Infested with crime, that's not a class. That's not a class of things. So what's going to be standard form? We're going to say some cities, and you could say a lot of different things here, but I'm going to say are places. Places that are infested with crime. All right. Now, what we're going to do is we got to diagram this again. 1, 2, 3. And I'm going to use C to represent city, and I'm going to use P to represent places that are infested with crime. And the way we diagram this, just put an X right there in 2. Okay, clear all. All right, number 9. Some stores don't charge high prices for trendy clothing. Some stores don't charge high prices. I'll write it for trendy clothes. All right. Now, this is not in standard form either. Now, there are a couple of things. First of all, our predicate term doesn't name a class. But notice also our copula is not in standard form. Remember, our copula is going to be are or is. Those are the Those are the two basic forms that we're going to use. A verb of being, are, is. And this is saying don't. So to put this into standard form, we're going to have to change the copula, and we also have to name a class and the predicate. So what we're going to say is some stores are not places that charge high prices, ... I'm not going to write the rest out. So notice here is our copula right here. Here is our subject term, and then all of this is going to be our predicate term. So now we're going to Venn diagram this, and here we go. We get our circle, our regions, 1, 2, 3, and I'm going to use S for stores, and I'm going to use P for places that charge high prices. And the way that we show this is, since it's are not, so store is equal to regions 1 and 2, places that charge high prices is 2 and 3. So what we do is we notice the region of overlap, and then we just scribble that out. And what we're saying is, look at this, are not. So it's are not, it's not in 2. So what's left? 1. So that's how we show that. Some stores are places that are not places that charge high prices for trending clothing. So that's how we diagram, that's how we put the sentence into standard form and then diagram it. All right. So then you were asked, so that completes that first part. So then you were asked on page 162, you were given a pair of Venn diagrams, and then you were asked to determine whether or not those diagrams are consistent. So beginning with problem number 2, you were given the following 2 Venn diagrams. One right here, and then this one right here. And you were asked to determine whether or not these two are consistent. And remember, when we talk about consistent, what we mean is the two propositions, it is possible for them to be true at the same time. That is what consistency means. Consistency is not the same as equivalent. Equivalent means they're true at all the same times and they're false at all the same times. Consistent means there's just at least one scenario in which the two propositions are possibly true at the same time. So look at what these two are saying, and first of all, you have to figure out what they're saying. This is saying some P, it's not saying that. Actually, it is. Some S are P, and this is saying no S is P. Are these consistent? And the answer is no, they're not consistent. These are actually contradictory statements that are making here. If you remember your square of opposition, these are contradictories. And if propositions are contradictory, they are inconsistent. So, all right. Then you are asked to do problem number 3. And here you are given the following 2 Venn diagrams like this. And are these consistent with one another? Well, let's look at what they're saying. This is saying some S are P. This is saying some S are not P. Are these consistent? Remember, consistent means there's at least one scenario in which these two statements are possibly true. That is possible. Possible, that's the operative word, for both of these to be true at the same time. Now, what this is not saying is, this is not the square of opposition. It's not asking if the first sentence is true, must the second one be true. We're not asking about dependence between the propositions. We're not asking if the first one leads to the second one. Rather, we're just asking, is it possible? Can we say, sorry, my eraser here is small. Is it possible to say, under some circumstance, that this one could be true and this one could be true? And the answer to that is yes. These two statements are consistent. It is possible for some S to be P and some S to not be P. These statements are in fact consistent with one another. Finally, we come to problem number 5. And here we have the two diagrams, S and P, and this is shaded in right here, and then this right here, S and P, and region number 2 has been shaded in. And the question is, are these consistent? Is it possible for both of these to be true at the same time? Well, what are they asking? Or I'm sorry, what are they saying? This is saying all S are P. This is saying no S is P. And these are not consistent with one another. They are, in fact, contrary propositions, not contradictory. They're not contradictory because even though if this one's true, this one's false, it's not the case that if this one's false, this one is true. That doesn't follow. It's possible that both of these could be false at the same time. Whereas when we deal with contradictory propositions, if one is false, the other is true. If one is true, the other is false. This one, when we deal with contrary propositions, is a little bit different. If one is true, then the other is false. But if one is false, then the other one could be false or true. So when we deal with, and in fact, that's why we don't have the arrow, because the arrow, you follow truth with the arrow. Oh, you can't see this, sorry. But my point here is these two are not consistent. These are, if you remember from your square of opposition, these are contrary propositions. It is, and again, you have to bear in mind what the meaning of the term consistent means. It means it's possible for two statements to be true at the same time. All right? Well, hopefully that makes some sense to all of you, because we're going to move to the final section of your homework. And it was on page 162, and on page, 166. And on page 166, you were to state the converse of each of the following propositions and then indicate whether the propositions and its converse are equivalent. So this was kind of lengthy here, but beginning with number 2, all stickers are scented. Now, I have to say, this is not in standard form, because technically speaking, this should say all stickers are scented things. So shame on the book for not doing this correctly. Well, the first thing we have to figure out is what is the converse of this. And remember, to find the converse, we just swap the subject and predicate terms. So we'd say all scented things are stickers. And are these two logically equivalent? Now, you could just remember from looking at the chart that they're not, but we're going to diagram them because you need the practice. And as far as this goes, let's do the first one. We're going to use S and ST. S for stickers, ST for scented things. All stickers are scented things. Well, how do we diagram this? Well, we mark the regions as before. Scented things is going to be, you know what I should do? I should do this down here. I'm going to use S equals 1 and 2. Scented things equals 2 and 3. And what we do is we identify where they overlap. Then we don't worry about this right here. We don't worry about the second region. And what we're saying is that all the S that exist in the world exist in 2. Now, how do we show this? We don't use an X because X doesn't mean universal. When you see all, when you see no, the only device you're going to use is shade. So how do you use shade in order to show that all the S are in region 2? You don't shade in 2 because that would show you that nothing's in 2. So the only thing you can do is shade in 1. And what this does is it shows you that all the S are in 2. Now, we move over here, and it's important that when we're doing the diagram, we keep the S and the ST in the same spot as this diagram. Even though scented things and stickers has been switched around in the propositions up here, we keep them in the same order in the diagram. So now what we're doing is kind of the same thing. ST equals 2, 2 and 3. Oh, good gravy. 2 and 3, and S equals 1 and 2. Now, it's important that we keep in mind that scented things is in the subject term. So even though S and ST remain in the same place in the diagram with the circle, we're going to switch the order in the proposition. So the areas that we're going to be concerned about shading are going to be 2 and 3. Why are we concerned about shading areas 2 and 3? Well, because we only are ever concerned about Xing or shading the subject term. We're not concerned about the predicate term. And what we do is the same as before. We identify the region of overlap and we disregard what's in the predicate. So now what we're saying is that all the ST in the world are in region 2. And if all the ST are in region 2, where are they not? They are not in region 3. They're not in region 3. So is the converse in this problem, or is it converse equivalent? And the answer is no, not converse equivalent. And this is something you could have drawn the diagrams, or you could just remember it, that when we're dealing with an A-form proposition, the converse is never equivalent. All right, now you're asked to do problem number 5. Problem number 5. Some books are not hardbacks. Some books are not hardbacks. I'm going to abbreviate that. So how do we find the converse of this? Well, keep in mind that's our are not is our copula, hardback is our predicate, books is our predicate. So the converse would be some hardbacks are not books. All right. Now you could just remember it, and so these are the converse of one another. I'm going to use 1 and 2 so we can keep them straight. 2 is the converse of 1, and 1 is the converse of 2. Now you could just remember that when you're dealing with an O-form proposition, the converse is never equivalent, but we're going to, you guessed it, diagram. So I'm going to use book right here, B for book, and HB for hardback. And we'll go ahead and write it over here just so we can keep it straight. 1, 2, 3, 1, 2, 3. All right, so what we do is we look right here. In the first proposition, book is in the subject term, and book is region 1 and 2. HB is the predicate term, and so that is region 2 and 3. And what we do is we identify the region of overlap, we shade in the 3, and then next we look at are not. And what we're saying is we know we're going to use an X because some, when you see some, think X. We know when saying are not, we don't put an X in 2. So if we don't put an X in 2, we've eliminated 3, we put an X in 1. Okay. And this shows us that some books are not hardbacks. Well, down here, when we do this one, notice that hardback is our subject term now. 2 and 3. Hardback is the subject term. And B is our predicate term. 1 and 2. So what we do is we identify the region of overlap. We eliminate this. And we're saying some hardbacks are not books. So are not means not in 2. We put an X here. And are these two propositions logically equivalent? No, they're not. The converse of an O-form proposition is never logically equivalent. All right, clear all. Continue. Number 6. Man, why did I assign so many of these? Number 6. I'm just kidding. It's good for you. So some poor, I'm just going to abbreviate this, poor neighborhoods are safe areas. All right, some poor neighborhoods are safe areas. Well, how do we find the converse? We swap the subject and predicate term. Some safe areas are poor neighborhoods. Now, are these logically equivalent? Is one logically equivalent with two? And you could just remember that when you're dealing with an I-form proposition, the converse is always logically equivalent. But we're going to, you guessed it, Venn diagram. You guys didn't know it was going to be this much fun when you signed up, did you? You had no idea. So I'm going to use PN for poor neighborhoods, safe area. Again, PN, safe area. And we have our regions 2, 3, 1, 2, 3. And we start right here. The subject term comes first, is 1 and 2. The predicate term, safe area, is 2 and 3. And what we do is we identify the region of overlap. We shade out that because we don't care. And we're saying some are. So since we see the sum, we know we're going to be using an X. And so what we do is we put an X right there in 2 because we're saying it are in 2. It is in 2, okay? It are in 2. I'm joking. Hopefully you can excuse my lame sense of humor. So I'm talking when I should be writing. So we come down to proposition number 2, and we notice that now safe areas is our subject term. So we're going to list that first, 1 and 2. Poor neighborhoods, that is our predicate term now. So we're going to list 2 and 3. We identify the region of overlap. We shade that out. And again, we're saying are. And we're saying some SARPN. So we say are. And when we see are, we put the X in 2. We're saying some safe areas are poor neighborhoods. And the question now is, are these two logically equivalent? Yes. I mean, these diagrams look identical. So they're definitely logically equivalent. Only got a few more left, people. All right, number 11. Some tornadoes move in a straight line. Now, first thing first, this is not in standard form. So before we can do anything, we had to put this in standard form. So what we're going to say to put this into standard form is, I'm going to write this over here just so we're clear. Some tornadoes are, I don't know what to call this. I'm just going to say things that move, in a straight line. So the first thing, that we can't even work with this sentence because it's not in standard form. So we had to put it in a standard form. So now what we have to do is we have to identify our subject term and our predicate term because we're going to find the converse. With tornadoes is our subject term. Things that move in a straight line is our predicate term. And to find the converse, we simply swap those. And so we're going to say, here's the converse. Things that move in a straight line. So I'm being lazy. Some things that move in a straight line are tornadoes. All right, so now we have our two sentences we can work with. And again, you might just remember that when you're dealing with an I-form proposition, its converse is always logically equivalent. But because we just have at this point, we love Venn diagrams so much, we're going to continue drawing them. So we're going to use T to represent tornadoes, and I'm going to use SL for things that move in a straight line. So how do we show that some tornadoes are things that move in a straight line? We simply put an X right there in 2. Come down here. Some things that move in a straight line are tornadoes. Again, this one might be a little trickier because you're kind of having to think in reverse to what you were before. But things that move in a straight line are regions 2 and 3. Tornado equals regions 1 and 2. What we do is we identify the region of overlap, we eliminate this, and we're saying it are. When you says it are, then you just put an X right there in region 2. So are these logically equivalent? Yes, sir. They are logically equivalent. Actually, I know I'm kind of making fun of some of this, but to me this is fun. So I guess I'm just, I don't know, I have a warped sense of what is fun. None of my children is a married person. Well, first of all, this is not in standard form. So we're going to have to put this in standard form. And this one's actually kind of tricky now that I should have thought about this one ahead of time. But first thing you're going to have to do is you're going to have to change the quantifier. We can't work with none. We have to work with no. So this is going to be really complicated, but something like the following. No child of mine is a, we could just say married person. I think that'll work. No child of mine, no sweet child of mine is a married person. No, sorry, being stupid. This is our subject, and a married person is our predicate. To find the converse, we simply switch them, and we'd say no married person is a child of mine. Any of you know that Guns N' Roses song? It's classic. All right, man, that looks like crap. I'm sorry. Child of mine. So are these two propositions, 1 and 2, are these logically equivalent? Now again, you could just remember that when you're dealing with an E-form proposition, they're always logically equivalent, but we're going to, you guessed it, diagram them. So I'm going to use C for child and MP for married person. And if you're saying that no child of mine is a married person, you shade this in, because then that shows that there's no overlap. It's empty. It's a void right here. All right, well, how about over here? What if you say no married person is a child of mine? Well, keep in mind that married person, since this is a subject term, we're going to list that first, and that represents 2 and 3. Child of mine is 1 and 2. So what we do is we identify the region of overlap, we just scribble out that, we're not concerned about it, and then what we're saying is we're saying no. So we're saying no, that means nothing. Nothing is in 2. So we shade that in. And are these two statements logically equivalent? The converse of no child of mine logically equivalent to no child of mine is a married person. Is that logically equivalent to no married person is a child of mine? Yes, sir, it is, most definitely. Those two are logically equivalent. All right, now, finally, I know the fun is about to end and some of you are really sad, but anyway, I'll stretch it out as long as I can if it makes some of you happy. Nothing you read on the internet is trustworthy. All right, well, first of all, this isn't even in standard form. Notice the quantifier is wrong. Trustworthy, that is not naming a class. Trustworthy doesn't name a class. So we're going to have to name a class of things. You read on the internet, that doesn't name a class either. So we can't really work with this sentence. So what we're going to have to do is say no, and I'm using the word information. You could have used a different, no information you read on the internet is trustworthy information. All right. So notice here we have our quantifier that is our standard quantifier. Information you read on the internet. That is our subject. Is our copula. Trustworthy information is our predicate. Now, we're going to just remove this sentence up here because we couldn't work with that because it wasn't in standard form. So how do we find the converse of this sentence? Well, we just flip the subject and predicate. So we'll say no trustworthy information. I'll put this in capitals since we're abbreviated. No trustworthy information is information you read on the internet. That is too complicated. I'm going to do like that. No trustworthy information is information you read on the internet. So basically I just switched the subject and predicate term. Now are these logically equivalent? And again, we just did one involving no, so you should know that when you're dealing with an E-form proposition, they're always logically equivalent, but we're going to do one better than that, and we're going to diagram this. So I'm just going to use information you read, IR for information you read, trustworthy info, and if we're saying no information you read on the internet is trustworthy, we shade in 2. So what if we do like this and we say information you read, trustworthy information, and we're saying no trustworthy information is information you read on the internet. Now we're having to work a little backwards here. We're going to use TI, and this is going to come first because it's first in this statement right here, and that's equal to regions 2 and 3. Information you read on the internet, IR, that's equal to regions 1 and 2. And what we do is we identify the area of overlap. We cross that out. And we say no. So no to 2. And if we're saying no to 2, we shade that in. So are these two right here, are these logically equivalent? Yes, sir. They are logically equivalent. So I know that was a bit much, but hopefully it wasn't too bad for you. If you have any remaining questions about this, please let me know. It's important that you understand how to do this because you are going to be tested on it, and a lot that we're going to be doing as we move forward builds on everything that we've been working on here.